Hello. Yeah, it's audible now. Takip, speaker is on. Takip. On है.
ये तो रिकॉर्डिंग दिख रहा है क्या?
YouTube में लाइव हो रहा है ना. Speak to him.
Hello, sir.
Stand and speak.
Sir, PK Singh, sir.
Yes,
are you now online,
yes,
sir?
yes, I am available. Yes.
Okay, good afternoon, sir. Now we are dear participants. Hello, dear participants. Good afternoon to all. Now in this today's session 2, now we are going to learn from Dr. PK Singh, who is the Director of Geological Survey of India, Lucknow Center, and he has a vast expertise in this regard, application of remote sensing and GIS in field of geology. As you know, the geology is also a part of our regular science. So since our students, they are dealing with the environmental concept, and I think it is related to our geology also. And with a special request, he has agreed to act as a speaker in this session, that principle of remote sensing in forestry, application of remote sensing in forestry. So now I am just briefing his biodata. So he obtained his MSc Geology from Banaras Hindu University, Varanasi. He was trained in special data handling from ITC Netherlands, which is a very renowned institute giving training in this remote sensing and GIS to many many intellectuals throughout the world. And we are fortunate to get him as a speaker, who is trained from ITC Netherlands. He got his PhD from neotectonics from Maharashtra. He has many awards in his to his credit. So he has got gold medal in MSc Geology from Banaras University, Hindu University. Professor Rajnath medal from BHU, and many recognitions he has obtained to his credit. And as far as the professional experience is concerned, so geological investigation in thematic mapping, remote sensing, GIS applications, environmental geology, mineral investigation. So he has to his credit 27 publications in national and international journals. So with this brief biodata, now I would request Dr. PK Singh to interact with our participants with his lecture. Thank you all. Please, Dr. PK Singh, please start your lecture.
Thank you, sir. Thank you for introducing myself to the participants. As you know, I'm basically a geologist. I'm working in Geological Survey of India, as you told. I have worked in Arunachal as well for 3.5 years. So in last August only, I got transferred from Itanagar to Lucknow. So I have seen different parts of the Arunachal as well. I have visited Pasighat 3-4 times. So It is really a pleasure for me to be part of this webinar, and I'm very happy to share my knowledge in this field. Definitely, I'm not from forestry background, even though the principles of remote sensing and GIS and how it can be utilized in the forestry, that part I will be dealing with. Definitely, it will be, I hope, quite informative for the students especially, and faculties as well. So I have planned my lecture in such a way that most of the part will be beneficial for the students, and some part will be specialized, that also will be good for faculties as well. So I have to share first the presentation, share screen. Yeah. Yes, second. Yes, is it
Slide
visible?
view.
Slide view, slide view.
Is it
Yes,
visible?
sir, it is visible, sir.
Okay, okay.
Please. Yes, sir, yeah.
So good afternoon, friends. I'll be dealing with different principles of remote sensing and then how it can be used in forestry. So starting with the principles of remote sensing. Uh, in brief, I just want to know nowadays, especially in geology, in forestry, and many more fields where we have to deal regionally. It is not like that you will be dealing with in particular area. Regionally, we have to deal. So remote sensing is very important, and without knowledge of remote sensing and GIS nowadays, it seems we cannot do full justice to our work. So it is imperative that all the students of forestry must be fair in the principles of remote sensing. Only then they will be able to use this tool in the forestry. So I'll be dealing those parts. So starting with that, first, simple basic. What are the basic principles of remote sensing? You know, it is need not to explain. Remote sensing means you have to take all the information, all the data, and convert into information from remote place. You don't have to touch the object. Yeah, go to the object very near to it. You have to take data without touching it from remote place using some sensors. So detection and discrimination of surface objects by measuring reflected or emitted radiation by a sensor remotely. That is the basic principle. In this way, data is collected in remote sensing. And you know, radiant energy that may be in the form of reflected energy or radiated energy is recorded with some sensor. That data is converted in the form of image, or many times we don't need image, rather we analyze data directly. So even then it is form of image. So you know what is radiant energy, what is reflected and radiated energy, that we'll be dealing with. Then different objects we have differently, as they return different amount of energy in different electromagnetic spectrum bands. So these things I'll be dealing. How they behave, what are the electromagnetic spectrum it is being used in different type of remote sensing, and other parts. Thereafter, you have to keep in mind this characteristic of material. Different materials radiate, yeah, reflect different amount of energy, and on that basis, that characteristic of objects is used to obtain different type of images, which is useful for different type of analysis. Yeah, starting with electromagnetic spectrum, you know, all the waves in the cosmos, yeah, universe, starting from one end to other end, that is known as electromagnetic spectrum. You know, this is the electromagnetic spectrum. Whole field is given you, starting from here to here. You see, simply keep in mind, from cosmic rays, gamma rays, X rays, then visible field, then microwave, then radio and television waves. This is one sequence. Here you have to be very cautious to keep in mind what is increasing from left to right, what is decreasing. You know, the speed of all the electromagnetic spectrum is constant. That is speed of light. Okay. In the left side, you know, somebody is speaking. Please put your mic off. Hello. Please put your mic off. Yeah, it's okay now. You know, the speed of light is frequency into wavelength. C is equal to n lambda. Basic classes, from basic classes you can remember. Speed of light, that is the speed of the electromagnetic spectrum, is equal to frequency into wavelength. And speed of these electromagnetic spectrum is constant. So as the lambda, that is wavelength, increases, the frequency decreases, because product of the frequency and wavelength is constant. So this is how it is increasing from left to right. Lambda is increasing, means wavelength is increasing from left to right. Therefore, frequency is decreasing. Okay. See here, this is the wavelength. This is for the visible spectrum only. Here wavelength is increasing. Here it is decreasing if you are going left side. And in the same way, energy of that photon, E is equal to h nu. You might recall, E is equal to h nu. Energy of that wave, photon, is equal to is proportional to frequency. H is Planck's constant, is equal to h nu. It means as frequency increases, the energy increases. Means those photons which are in the left side, they have more frequency, more energy. Since they have more higher frequency, so they have more energy. As you go right in the right direction, the energy decreases because frequency decreases. So this principle you have to keep in mind. Only then you will be able to understand in which band data is collected, what is the benefit of this. It will be coming that next slide. So here you have to keep in mind lambda, that is wavelength, is increasing towards right, means frequency is decreasing towards right. If frequency is decreasing, energy is decreasing. Okay. Now coming to next. Yeah. Energy interaction in the atmosphere. See, when actually most of the time solar energy is used as a source for remote sensing data collection. When actually there are two types of sensors, one active sensors, other are passive sensors. Active sensors create their own energy and record its reflection, and for passive sensors they record the energy which is mainly solar energy. Many times radiant energy also there. They don't use their own source of energy. So active and passive, the two types of remote sensing is there on the basis of the energy they are utilizing to collect the data. See here, what happens when some solar radiations comes. Actually, some part is absorbed by the atmosphere. Rest part is transmitted, which comes to the ground surface. But while transmission, some part is scattered. You know there are different type of scattering, like Rayleigh scattering, Mie scattering, or non-selective scattering. Some part of the wavelength is scattered. The remaining part is transmitted to the ground surface. When it comes on the ground surface, Again, some part is absorbed by the object, which is re-emitted later on, and some part is reflected back. So that reflected part is recorded by the sensor. Yeah, apart from that, this is the 100% transmission. How the part, what fraction of the part is transmitted, and one part is absorbed, the remaining part is transmitted. So this is the graph showing the transmission. It means here, see, this is the range where a lot of energy is transmitted, which reaches up to the ground. There is one gap. This is another gap. This is another gap. Means here the energy, most of the energy in this spectral zone, means from this wavelength to this wavelength in micrometer, 6 to 8, it is not reaching the surface. So definitely it will not be reflected back. So if you want to take data in this spectral band, we won't be able to take anything. So you have to select these ranges. These are called atmospheric windows, because atmosphere work as a window for this spectrum only. Rest part is not reaching to the surface. So definitely if you are recording those energy, it won't reach to the sensor. So these are called atmospheric windows. So you have to, if you are going to collect data, you have to look for the atmospheric windows in which the transmission is maximum. Okay. This part actually I have explained in that one. What happens? See, first requirement for remote sensing is energy to illuminate the object. How we are getting this energy? Either it is solar energy or active sensors are there which give their own energy to be recorded. If it is solar energy, then what happens? Some part of the some part is reflected from top of the atmosphere, definitely. Some part is absorbed by the molecules, aerosols in the atmosphere. Whole part doesn't reach on the surface, and some part is scattered. The remaining part falls on the surface, as I explained. When it comes to the surface, means you are interested to see the different objects on the Earth's surface, or different part of the Earth's surface. Then when it reaches on the surface, remaining part is radiated, which also pass through part of the atmosphere. Means after this absorption and scattering, that is transmitted to the Earth's surface in the form of some radiation. When it reaches on the Earth's surface, again some part is absorbed and some part is reflected, या radiated जिसको कहते हैं. This part is recorded by the sensor. यहाँ पे देख ले आप, same thing I have shown in the this image. Yeah, I have already told active sensor and passive sensors. Passive sensors, they record the energy which is coming from the Earth's surface. Either it is reflected back light or radiated light. Yeah, spectrum. Radiated, what is radiated? Some part is coming here, immediately it is reflected. That is reflected part. And in some band, spectral band, actually Earth's surface objects many times absorb the light. Later on, they emit the light, but there will be some difference in the wavelength of the absorbed light and radiated light, emitted light. Then passive sensors record this also, if it is radiated energy. So either it is reflected or hold the radiated energy, that is recorded in by the passive sensor. And for active sensors, they throw their own energy, it reacts with the surface, then come back and it records total how much impulse was sent, how much time it took to go to the Earth's surface and came back, Accordingly, the total height and other characteristics are recorded. This is the basic principle. Okay. See, now most of the time when we are talking about multispectral remote sensing, then this range of visible, this is visible range, thereafter some near infrared band and thermal infrared band. This is the range in which multispectral remote sensing is done. It means in multispectral remote sensing, all the images are created by the recording of the energy coming from this spectral band. Spectral band means the wavelength zone, you can say, from this wavelength to this wavelength in most of the multispectral bands. They use only this zone, but other type of remote sensing is also there, like microwave remote sensing, in which other microwave spectral band, actually it is 1 centimeter to 100 centimeter. If the wavelength is from 1 millimeter to 1 centimeter to 100 centimeter, 1 centimeter to 100 centimeter, then it becomes microwave remote sensing. And actually you can think what will be the problems in recording waves from this range and this range. Then you have to go to the first slide where I explained what is the energy of the waves coming from this zone. This is quite, here lambda is quite high, quite large. It means they have very low energy, and here energy is very high. So recording energy in this zone is comparatively easier. Actually what happens, those sensors, in sensors different detectors are there. They record the energy coming from that zone. See here, in one sensor, actually there are different sensors for different bands. Simply take example of list 3. In list 3 there are 4 bands. Okay? First band records the waves which are of the green visible range only. It means whatever red light coming here, or blue light, or any other light, it is a sort of you can say it doesn't allow other wave to enter into this sensor. It records only green lights. And second band, it records only red light. In that way, near infrared. So if different sensors are there, they are blind for other spectrum part. They record only that part for which they are made. So suppose one sensor, how it records? Whatever energy is coming to this sensor, it activates the detectors, and the amount of energy it is receiving, that is recorded in form of some number. How computer writes, it is converted to that. Actually, I will be dealing what is radiometric, what is spatial resolution. There I will be explaining. So whatever energy is coming to that sensor, it records it in the form of number. In that way, images are stored, created and stored. So in this zone, it is easier to have, if suppose you are taking from a small area, total energy is coming, it is activating your sensor. If you are taking here blue band, blue waves, then blue waves have comparatively much higher energy. So from a smaller area, they will be able to activate your sensor. But for the same area, if you are taking near infrared or thermal infrared, then their wavelength is quite large. so its energy is low. So that from that small area, that energy may not be able to activate the sensor. So it will feel that nothing is coming. So you will have to increase the total area so that the total energy coming from that pixel may activate the sensor. Therefore, the spatial resolution of the bands when you are coming from left to right is increasing, decreasing. Sorry, decreasing means pixel size will be increasing because it doesn't get enough energy from that small area to activate it. Therefore, suppose you are taking one example I am giving for ester data. Rather, I will take later. I will explain later. Okay. So, what is microwave remote sensing? If you are using the waves of this range, then it is microwave remote sensing. Otherwise, generally we use in common practice we use multispectral data. Okay. Then passive sensors, you know, their radiometers are there. They simply record the energy coming from that object, yeah, that part of the Earth's surface. Inactive sensor, imaging like imaging radar, where it sends its own energy, which comes back and recorded. These are bands. Actually, if you are using radar data, then which part of the frequency it is using, and that way it is known as S band, C band, X band. In that way it is named. But this type of band name is not for multispectral. There only band name you have to recall which band correspond to which part of the spectrum, because without that you won't be able to use the data properly. Okay. I'm giving you some names which actually these are some emerging fields. Some of you would be doing work in coming days. Some students from this group, I hope they will be working in future in this high-tech parts of the remote sensing, that is hyperspectral remote sensing. Actually, in multispectral, there are definite number of bands. For example, you know, in list 3, we have 4 bands. If you are going to use ETM data, so 11 bands like that. It is TM, thematic mapper, maybe some lower bands. If you are using that aster data, it has 14 bands. But when there are a lot of bands with a discrete, very small and narrow spectral ranges, then it is known as hyperspectral remote sensing. In remote list 3, you have 4 bands, and in ester you have 14 bands. If you are going to take hyperspectral data, it may have 220, 236 like that number of bands, and the width of the spectrum is very small. It is 5 nanometer to 10 nanometer as for various types of data. So it definitely will be giving you more information to differentiate between different type of objects. Suppose you are using it is for forestry. If you are interested to map different species, if you are going to map species level, then you will have to use hyperspectral remote sensing data. But still a lot of work to be done in this field. Though India is very developed as per the remote sensing science, but still we are not generating good quality hyperspectral data yet. Some experimental data is there, but high quality hyperspectral data we are not generating. If you have to work, some agencies of NASA and other institution of other countries, you may purchase some part actually for experimental basis, for study purposes. Hyperion data is available. Hyperion hyperspectral data for certain steps has been made available. That is only to learn how to use it. But if you are interested for your particular data, you will have to purchase very costly data. So this is difference between multispectral and hyperspectral. Hyperspectral में the spectral width is very narrow, that is 5 to 10 nanometers, and bands will be quite high. Okay, and how it works? See, this is the spectral signature. Means how the absorption and radiation is there. That is, every object has a peculiar typical type of this spectral signature, and this spectral signature is compared with the other parts of the area, and accordingly information is gathered ki whether this particular pixel corresponds to this known hyperspectral signature or not. Accordingly mapping is done, analysis is done. So you'll have to keep only in mind what is spectral remote sensing and how it is different from the multispectral remote sensing. In that way, in future you will be studying and doing some work, I hope, in spectral remote sensing. Okay. Sorry. When from different sensors the image data is produced, then you will have to do some analysis to extract maximum information you are interested in. See, these are 4 bands of 1 degree sheet, rather it's a topo sheet. I have shown band 2, band 3, band 4, band 5. You have to know what is the data source and what are the spectral width, spectral bands for different bands, spectral information of different bands. Using these bands, you will be making a lot of things. See here, band 2. Oh, this is list 3 data. See here, band 2 is green. Band, actually, why it is band 2? For list 3, you know, there are 4 bands. First band is known as band 2. First band is known as band 2. Second band is band 3, then band 4, then band 5. Why band 1 is not given the name for the first band? Because the first band, spectral range of the first band is green. Otherwise, it should be blue. First band in general, when it comes to your mind, you will think first band is blue band. But blue band, it is not, this image has not been taken. So first band is band 2, which corresponds to green zone. Second band, red band. Third band, near infrared, and a fifth band is थोड़ा सा near infrared से और right side में जाता है. So these are the 4 bands of list 3. If you have collected, okay, if you have collected the remote sensing bands, then you can do a lot of analysis. How it is done? For students, see, by now I am sure you might have been told about the structure of data. There are 2 types of data. One is raster data and there is vector data. All those data which are written in the form of grids, and these grids have 3 information. Suppose this is one band. So you are taking this grid. So computer writes only 3 things for this grid: X, Y, and Z. X, Y means its position. Where is the position of this pixel? And Z is the energy, record of energy. If it is the sensor has recorded some energy from the ground surface, that amount of energy is written in the form of some calibrated number, because computer writes only 0 and 1 binary numbers. So to express whole thing has to be written in the form of binary numbers. So it will on the basis of radiometric. Radiometric means how much number it can store. You can remember 1 bit data. 1 bit means 2 power 1. 2 power 1 means 2. That image, if it is having 1 bit, it can store only 2 information. 1 is 0 and there is 1. Okay. Suppose it is 8 bit. 8 bit means 2 power 8. 2 to the power 8, which is equal to 256. Most of the data you download from internet or anywhere is 8-bit data. Means it can write 256 types of data. Starting from 0, it will write 0 to 255. Total 256 ho gaya. So if it is data is 8-bit, then it can write 256 characters. So if you are writing anything in grayscale, you will be writing in 8-bit. But nowadays some data like Landsat 8, I will be explaining later. Landsat 8 free data, OLI data, up to Landsat 7. In Landsat 7 image sensor was ETM plus, that is 8-bit data. But Landsat 8, the image sensor is OLI, Operation Land Imager. That is also freely available. OLI data is 16-bit data. It means it can write 256 into 256, which is equal to 65,000 something. So 65 plus 65,000 plus type of information it can write. So that is radiometric resolution of data. If it is 8-bit or 16-bit, means how much type of data it can write, that is radiometric resolution. So I will explain different type of resolution later on. So this is the structure of raster images. And in vector image, what happens? In vector image, suppose you have to store one line. In vector, if it's straight line, it will store only two things: x, y of this place and x, y of this place. Only two information it will store, and it will add a line between these 2 points. To write this, if you have to write in a raster image, you will have to take this amount of area. It has to be converted into pixels, and information for each pixel is to be written. Therefore, the size of raster images are always very high in comparison to vector. And the thing here, line is there. Here there is no line. One grid is one square. If you zoom a vector map, line remains line. How much you are zooming, line will remain line. Its thickness won't increase. So that fuzziness comes, it won't come here in vector data. In raster, after a particular resolution, its resolution will, you won't be able to see anything, it will be hazy. That is difference between raster and vector data. So all the remote sensing data, that is collected in the form of rasters. Okay, so this is the data structure. Suppose 4 bands are there. One band is here, second band below that, third one below that. There are different types of algorithms, techniques, how this data raster images are written. That is not needed to explain here. You have to keep in mind all those data are in the form of raster. Rasters are only grid pattern data, where Z value is the amount of energy, that is radiation energy, radiant energy recorded by the sensors. Okay. Yeah. Then image data characteristic. You must know what type of data you are interested in, what type of data you have taken, what are the characteristic of those data. You know, radiometric data I have explained. What is the bit size? It is 1 bit, then only black and white you will be able to see, 0 and 1. If it is 8 bit, it is gray scale, light to dark. If it is 16 bit, more than 65,000 number of information you can store. So only that is radiometric resolution. Spatial characteristic. What is spatial resolution? The spatial resolution means what is the smallest part you can see using that image. High resolution means the pixel size will be smaller, means you can differentiate between two objects which are quite close to each other. Suppose most of the time by ETM data, what is the spatial resolution? It is 30 meter. It means all those information which is in the 30 by 30 grid is read as one information. So any object in that 30 by 30, if it is smaller than that, you cannot differentiate between them. Had the spatial resolution 30 meter, you could have differentiated those objects which are lying 10 meters away from each other. So spatial resolution means the ability to distinguish the smallest objects, distinguish objects from each other, the smallest objects. So most of the time it is 10 meter, 30 meter. Panchromatic bands may the spatial resolution comparatively high. I will explain why. So this is spatial resolution characteristic. Other is spectral. You have to recall the wavelength range of that band. That is spectral resolution, spectral characteristic. If you are talking about characteristic, suppose you are taking band 1 of list 3, band, it is known as band 2. See, band 1 hai, but it is written as band 2 because it is falling in the green zone. तो कितना से कितने के बीच में it is 500 something से 600 nanometer. This is the spectral characteristic of this band 2, which is band 1 really in list 3. So what is the wavelength of this band? That is spectral characteristic. And resolution means how narrow is the band. If narrower the band, the resolution is higher. That is why for hyperspectral, the resolution is very high. The width here, the width is 100 nanometers. There it may be 5 nanometers only. From 500 to 505, 505 to 510, 10 to 15, 15 to 20. The bands are very narrow. So all those characteristics are recorded in these spectral ranges. So the narrower the spectral range, higher the spectral resolution. In the same way, smaller the pixel, higher the spatial resolution. So these are 3 spectral characteristics. A 4th one is temporal. You are interested to detect the changes, you have to have higher number of bands from different time periods. Only then you can you will be able to compare the images of different times. So that is temporal resolution. In forestry, temporal resolution is very important along with other as well, because you have to have a lot of remote sensing data temporally, so that you can detect the changes, how the forest is increasing, how is it decreasing, and other analysis you can do. Okay. Then comes the I am unable to remove this strip. It is visible here. Okay. Okay. I have shown some characteristic of different data. First of all, I want to say one thing: the remote sensing data name, how it is named. Actually, remote sensing data is named on the basis of its sensor. Sensor name gives the characteristic of the data. Actually, LIS3 is one sensor. It is on the platform. Platform means satellite. On which satellite it is fixed. That satellite is not important. Rather, that sensor is important. So LIS3, if you want to have a very old data of LIS3, you will be getting IRS1 LIS3, IRS2 LIS3, and now it is IRS-P6 LIS3. Means on different satellites, the LIS3 has been put. So if you are talking about LIS3 data, you don't have to bother about the platform on which it was fixed. So remote sensing data is named on the basis of the sensor, like LIS3 data, ETM plus. See here, ETM data, we call ETM plus data. So ETM plus is the sensor which was fixed on the Landsat 7. Landsat 7. Before that, it was Landsat 6, on which it was ETM. Before that, thematic mapper on Landsat 5. Before that, MSS data, multispectral scanner data, that was on Landsat 4 earlier. In that way, on the basis of this sensor, the data's name is held. MSS data, TM data, all these data are freely available now. In this chain, the latest data is ETM. After ETM plus, it came OLI data. OLI data. That is Landsat 8 data. The difference between ETM plus and OLI, actually they have put one ultra blue band in OLI, and the spectral resolution has been radiometric resolution has been enhanced from 8-bit to 16-bit. This is difference between ETM plus and OLI data. Spectral band C. This is the for band 1, band 2, band 3, in that way. And one band which is having a wider spectral range, that is called panchromatic band. Panchromatic band has always higher spectral zone. Okay, higher spectral width. See here, 0.5 to 0.9. From 0.5 to 0.9, 1, 2, 3, 4. 4 bands, band 1, 2, 3, 4. All waves incorporated in one recorder, which has recorded all the waves from here to here in the form of panchromatic band. Why panchromatic band is created? Because panchromatic band has higher spatial resolution. Why? As I explained earlier, you might recall, suppose this is the spectral, this is the pixel size of your sensor. Okay? You are recording only for band 1, you are recording only blue waves in one sensor. Okay? For second band, you are recording from the same pixels, same part of the Earth's surface, only green colors. For this sensor, other lights are not allowed to enter into this sensor, only green for band 2. For band 3, only red is allowed. Okay? So at least minimum amount of energy should be there to be detected by the sensor, and your pixel size is fixed. इतने से ही जाना है energy. So if you are decreasing this pixel size, the energy coming from this, that area may not be able to be get detected by the sensor. So it will be blank. It will be blind. But if you are taking this, all the waves from blue, green, red, near infrared into one sensor, so definitely if you are taking all the energy, 4 bands, so some part of some energy will be definitely coming, because your spectral range has been enhanced. So that same area will be able to get the sensor detected. So in that case, if you are taking even smaller area, it will be recorded. So in panchromatic bands, the spatial resolution will be high. For example, ETM plus the spatial resolution of other bands of the visible range, and near infrared, that is 30-meter resolution. And but for panchromatic band, it is 15 meter. See, then how it can be used? You can make different color composites using these bands and merge it with the panchromatic band, so it will take the spatial resolution of pan band. In that way, panchromatic bands are very helpful because it's their spatial resolution is much better than the other bands. See here, 15 meter spatial resolution. See, all characteristic for the bands data is given. What is the sensor? What is the swath width? Means area covering by the sensors. Then revisit time, temporal data, 16 days, spectral bands, spectral characteristic, spatial resolution, everything is given. If once you download data, apart from that data, one metadata for this data is available. That in that file, every information is given. I hope I am clear about this. In that way, only then you will be able to use these data. Then other is, see, Aster data. There are 14 bands. One thing I would like to say, in Aster data, its first three bands have based spatial resolution for any freely available data. It has 15 meter. Okay, Aster data is the best freely available data with respect to its spatial resolution. It is also freely available. For LISPO, they have added one panchromatic band. Uska spatial resolution is actually 5.8 meter hai, 6 meter it is written. That is LISPO. Aster data, different characteristic of Aster data is written. Band 1, band 2 in that way. You will be getting this information very easily when you search anywhere. And you can download all this data freely, and with metadata where every information is given. In that way, you will be able to choose which band is to be used for what purpose. Later you will be coming in that sections what is use of different bands. Okay, yeah. Now I hope you have got basic thing, what is the structure of data, then how to do some image processing. Image processing, what is image processing? Simply to make some changes in the image to extract maximum information you are interested in. Okay, data say you will be converting into information, extracting information. Somebody as a geologist, I'll be interested to know what is the type of lithology, what are the major lineaments, what is different geomorphic units, how some structures can be picked up from this type of remote sensing data. And a person from forestry will be interested to know what is the characteristic of forest there, what type of plants, trees are there, what is how the forest is depleting or increasing, what is the health of the plants at different times. Those type of information you'll be extracting. But before that, you have to do some image processing. Suppose you are downloading different bands, different data of area, and your area is quite bigger. So how to merge those data to make one, in those things I'll be dealing in SART. Mosaicing of imagery. Suppose one imagery you have downloaded here and the imagery here, and you want to mosaic. Then you will be making one unit out of different bands, different images. That is mosaicing. And there are different freely as well as paid softwares. specialized softwares which will be used for doing this. So one software, that is ArcGIS. Most of the institutions are having now ArcGIS. So I'll be discussing on mostly in that context. But apart from that, like QGIS, that is a free software. Quantum GIS, that is free software, but most of the things, rather everything what you can do in ArcGIS can be done in QGIS as well. But these are they are GIS softwares. A specialized remote sensing softwares also, so they are like ERDAS, NV, you might be using some of you. But most of the things nowadays can be done in ArcGIS as well. But one good thing is that if you are doing these things in ArcGIS, you will be knowing what exactly I am doing, which data I am using. So basic concept is required there. Though basic concept is required everywhere, but here you have to do manually many things. And in specialized remote sensing softwares, it will be doing automatically. You have to simply specify these are the different bands. I want this type of product. So you can choose any software. Mosaicing of imagery, extraction of area, say one topo-sheet. Suppose whole area, this is degree sheet you have taken, you are interested in particular area. You can do some clipping, some other thing. If you are interested to take the information on the basis of your district level, you can extract that part also. Then composite, how to make composite bands, what is span sharpening, what are band ratio, those things I'll be dealing with this. This is simply mosaicing. I have taken 2 degree sheets. I am interested in that part of the area. I'll be doing mosaicing, then clipping the area of my own interest. So you will be doing mosaicing in all software, ArcGIS, LVIS, NV, QGIS, even LVIS. One software, free software, LVIS is there, ITC's software. There everything can be done. So mosaicing you can do, same word, yeah, sometimes this term differs from one software to other software, but everywhere this facility is available. So mosaic areas, extract your own area of interest. It is done, okay. Then comes composite bands. See, as per the color composite making, means each band is having, if you have one band, whatever may be the radiometric characteristic resolution, means what is the bit size, doesn't matter. Whole image will look gray in the different shades of gray, because it has only one band. You need at least 3 bands to make color composite. So you have different bands, take 3 bands, yeah, take maximum all the bands simultaneously, but you have to select 3 bands to make a composite, color composite. And this color composite, here you have to have fair knowledge of the spectral bands, because band names changes as per the sensor name changes. So band 1 of one sensor may be different from the band 1 of the other sensor. So instead of keeping in mind band numbers, you have to have fair knowledge of the spectral range of that band, because on that basis you will be selecting data for analysis. So here all the bands you make a composite, then select 3 bands to give color as per your wish. You know, in color composite, there are some standard names. One is true color composite. True color composite means it will be giving you the feeling of true color, how the actual object looks. Suppose one forest, you are looking from top of the forest from the sky, how actually it looks. If you are preparing that type of composite, then it is true color. True color composite you want to make means you have to give the color corresponding to that band, which is actual band. See here, band 3, band 2, band 1. If you are, I am taking it as ETM data. Why I am taking ETM data, I will tell. ETM plus, ठीक है? In ETM plus, first band is blue band, second band is green band, third band is red band. Okay, if you are giving red color to red band, green color to green band, and blue color to blue band, then it will be true color. जो waves जैसी आ रही हैं वही color हम दे रहे हैं, तो definitely it will be true color. Here 3 to 1. But one customary has been started and being used, that is false color composite. इसमें many a times people are interested to know what is the vegetation, to highlight vegetation in the form of some color. This combination has been made. Actually, this green vegetation reflects maximum light in near infrared band. You know, in near infrared, maximum light is reflected back in the which is band 4. So if you are giving red color to band 4, it means maximum area where the vegetation is dense, maximum vegetation is there, that will look red. Therefore, this 4-3-2 combination has been standard, in standard practice to make false color composite. Especially, it highlights the vegetation. So, where maximum vegetation, it will look dark red. Now, my one simple question. See, this is for ETM. Okay? Accordingly, you have to choose bands if you are using different sensors. If you want to make true color composite using list 3 data, then what will be the band combination here? If you want to make true color composite using list 3 data, what should be the color composite color combination? You might have thought something. Answer is that you cannot make true color composite using list 3 because I told you there is no blue band. Okay, so if you want to make true color composite, you have to take other data because we don't have blue band in list 3. That is why I asked. Okay, and the combination pseudo natural color, that is a short wave infrared. Short wave infrared, actually here short wave infrared, short wave infrared band is given red. So, and infrared will be 4, band 4. So here again, hold the band 4, see, band 4 is near infrared, and plants or vegetation gives maximum reflection in this near infrared, and you are giving near infrared green. It means all the vegetation covered areas, high density vegetation areas, they will look green, and green is the color of the vegetation. That's why it is called pseudo natural. Actually, we are not taking the green part as green, rather near infrared as green. That's why it is called pseudo natural color. So these are different color composites you will be preparing for taking different information. See here, I have taken blue you have to select red, green, blue, and select green band. Which band you want to give red, which band you want to give green, which band you want to give blue. Accordingly, your color composite will be prepared. Once your color composite is prepared, your data is ready for taking information. Then pan sharpening. I already explained that pan chromatic bands have better spatial resolution. So if you are creating one color composite using other than the pan chromatic band, then merge it with pan chromatic band. The color will be from your multispectral bands, and spatial resolution will be from your pan chromatic band. So spatial resolution will be enhanced. So pan sharpening, pan, different in softwares, different names, terms will be there, but everywhere this technique is available. In ArcGIS, it is written as create pan sharpened raster dataset in ArcGIS. In ERDAS, it is pan sharpening. In that way, different names are there. Ultimately, your data is ready for analysis. One thing more before I want to explain. Yeah, here. Your data, when data is generated, it is stored as raw data. Thereafter, some sort of corrections are done. Many times, this ortho rectification is there. Means those corrections, it should actually fit the exact place on the Earth's surface, because when data is collected, it is in the geographic coordinate system. Then it is to be properly what you say. It is to be projected. Yes, it is to be projected. Actually, when data geographic coordinate system, geographic coordinate means it is a part of the curved Earth surface. Then it has to be, if you are doing in smaller area, that data is to be projected on a plane. For that, you have to use different projection techniques, so that that part exactly fit on the Earth's surface. Apart from that, some atmospheric corrections is done. As I told, on the sensor, see, this is your sensor, some radiated some reflected radiated energy from the atmosphere goes to the sensor. Actually, we are interested in the energy which is coming from the object, but some scattered light, some reflected light, that is also going to the sensor, and that energy is recorded in the form of DN value. So some corrections are done to remove all those things which are coming from other sources. So suppose you are interested in only reflected data. So from DN data, what is DN data? When you download any data, it is written in the form of DN values. As I told, X, Y, Z, Z is the DN value, and this DN value depends on the radiometric resolution. Suppose it is 8-bit, so it will be from 0 to 255. See, this DN value, suppose here it is 100. 100 means this is corresponding to the energy received from that pixel. But this 100 is not exact value of the emitted light. So that reflected light, radiated light, so that 100 is actually representing something. So in many calculations, you need to convert this DN value into radiance and reflectance. Most of the time, we are interested in reflectance data. So this DN number is converted into reflectance data. But for that, different formula are there. Actually, that needs one more elaborated lecture to explain how this DN data is converted into radiance and reflectance. But nowadays, luckily, most of the data is this reflectance data is also available. So you can download directly the reflectance data, or simply you have to send one mail. Suppose you are downloading OLI data, ITM data to NASA. If you are writing one email, I am interested in the reflectance data of that particular area, in one day they will system calculates and sends. So you will be getting that data also. Otherwise, taking metadata information, you can convert DN data into radiance and radiance into reflectance. That part you have to study. Otherwise, simply you can download, because most accurate information comes from the reflectance data, because that is the characteristic of that particular object. In DN value, in other data, other scattered radiated parts are also giving some enhancement to the total energy, but actual characteristic is reflected by the reflected radiation. So you are ultimately interested in reflectance data. Once your data is ready, then you will be doing different type of analysis to extract information. For example, band ratio techniques. Using band ratio techniques, you will be able to extract a lot of information. For example, see, I have done it. This is quite useful technique, remote sensing in geological investigations also. I have prepared one map where maximum clay is deposited in that particular area. By simply band ratio, different established band ratios are there. In that way, you can calculate. In the same way, different vegetation index techniques are developed, which are solely used in forestry. So I'll be discussing those things now. If some confusion is there, some query is there, definitely you can ask me. Otherwise, in later part, definitely you'll be asking. Application of remote sensing in forestry and agriculture. See, different information you can extract using terrain analysis, forest management, temporal changes, recultivation, forest inventory preparation, forest cover type discrimination, mapping of forest fire, mapping of cleared areas, health of vegetation monitoring, basin drainage analysis. These are the general classes in which remote sensing data can be used in forestry. One thing I want to make clear, actually in commonly used remote sensing data, there are two types of data. One is multispectral band data, in which how it looks, what is the characteristic with respect to different spectral bands, I have explained, that is recorded. In other data, only height data is recorded, that is digital elevation models. So a lot of information you can extract using digital information data, that is also remote sensing data. And second type of data from multispectral and hyperspectral, that type of information you'll be using. So both has different type of utility. If you want to do terrain analysis, you have to have digital elevation model data. Thereafter, you can drape it over with the multispectral data information you have taken out. So for digital elevation model, different data is available, like SRTM data. You must be using Cartosat DEM data or GDEM, that is Aster digital elevation model data. These data are available. Then other things are there. Then coming to forestry application of remote sensing can be classified into three groups. One is reconnaissance mapping. Reconnaissance mapping means how it looks with time to time. That is forest cover updating. Suppose this year, this is the forest area. Next year, how it is increasing or depleting. Then depletion monitoring. Most of the time, unfortunately, depletion is more. But nowadays, with efforts of different agencies, different people from your side, the forest is increasing also. So that type of recording monitoring is to be done. That will be under reconnaissance mapping. Then forest cover type discrimination. What type of forest is there? For that type of discrimination, this study is done. Then in commercial forestry, harvest information, when the harvesting time is there, whether trees are fruits are ripen or not, that type of information can be calculated. Inventory for timber supply, what is the total density of timber in that particular area. Forest type, vegetation density and biomass mapping, that can be done using remote sensing techniques. Nowadays, a LIDAR technique is very helpful in biomass calculation. LIDAR, that will be active sensor in which laser beams are used. So that is also very good technique for biomass mapping. Species inventory. Here, if you want to differentiate different species, then you'll have to use different type of hyperspectral data. Yeah, sometimes multispectral also used, but they may not be so accurate as hyperspectral data. Tree generation of forest. Then environmental monitoring, quantity, health, diversity, deforestation, coastal protection, forest health, these things under environmental monitoring. So all these things can be using this remote sensing data. Yeah. See, in application, one thing is image classification. You will be doing, if you are not doing, you will have to do in different stages of your work, different stages of your study part. See, definitely if you are taking one multispectral image, it has different spectral signatures for each and every pixel. And that spectral signature is characteristic of particular type of vegetation if you are using it for forestry. Means different type of forest, yeah, land use, suppose it is bare soil or different type of land use, it has different spectral signatures. So on the basis of spectral signatures, you will be classifying whole image. Thereafter, it has to be validated in the field. See, validation of your work is very important part of your project. Whenever you are extracting some information, whether it is matching with the information from the ground or not. If it is not matching, you have failed somewhere, you have not done things properly, our data has not been used properly, or there may have some limitation of the data. A lot of problems, causes will be there behind that. So for every result, validation, field validation is must. So this is part of one exercise. So you will be classifying. There are two types of classifications of image data. One is supervised and there is unsupervised. First take unsupervised. Unsupervised is solely on the basis of spectral signature, spectral characteristic of the whole image. So it will be classifying whole image automatically. Suppose you are interested in 5 classes, 6 classes, 8 classes, 5 hold the topo sheet, take 1 unit. So it will be classifying whole the area on the basis of a spectral characteristic. Spectral characteristic means the energy emitting from that particular pixel, which has been converted into form of DN value. If you are using DN image, then DN, if you are using it converted radiance or reflectance data, it will be the Z value will be reflectance or radiance. So here, suppose DN raw data you are using, then what happened? It will classify, suppose whole it is 8-bit data. So DN value will be ranging from 0 to 255. Suppose you are taking ISO class, then 10 classes. So it will divide all the 256 classes into signatures into 10 classes of equal interval, and it will make different 10 classes. Then you will have to think what is this class, what is this class. But many times it is not of much use. Therefore, you have to have another good technique that is called supervised classification. In supervised classification, you give some information about your area to the system. Yes, I know this particular color is representing that particular vegetation. So you are training the system. Yes, this is the information I have. So for that, you have to take in different softwares, same thing is there. You have to make different polygons of one particular, one color. You know, using some ground truth, yeah, some other known information. Yes, this is particular area. This is, I know this is one softwood, yeah, whatever hardwood I know. So make one polygon and train it as the one particular use. Then take other color, give it other name, you know. In that way, you will be making different classes. Then system will search for those spectral signatures from whole the image and classify it as per your information given to the system. That is called supervised classification. It is widely used in classification of forest. So you will be doing sometime, you must be doing. This is supervised classification. Now coming to different vegetation indices. This is widely used and most varied field nowadays in different fields, actually, not only in forestry, even in geological investigations, we use such type of band ratio techniques to get information, sometimes up to mineralogy level. This on the basis of mineralogy, we will be able to detect what will be the rock type, because rocks are combinations of different minerals, and the proportion of different minerals, we conclude, yes, this particular area is rich in this type of rock. So same way here, I think it is more useful in forestry, because as my personal experience, I have worked in different high altitude parts of Arunachal in international border areas, which were not mapped earlier. And we tried to map that area using different remote sensing techniques. But for geological operations, you have to have the information on the surface, ground surface. But most of the area in those northeastern regions is thickly vegetated. Where vegetation is less, even then thick soil cover with some bushy, grassy area plants are developed. So we are not able to use this remote sensing techniques in many parts of the Arunachal Pradesh area, northeast, where thickly vegetated part is there. It is good for those areas in semi-arid, arid regions where bare rocks are available. For geological investigation, those areas are good, but for forestry, definitely you have to, you are interested more in the foliage and top of the reflective surface. So it is very useful in that field. But in other parts also, in other type of information, we use remote sensing in these vegetated areas also, because total terrain condition, drainage condition, drainage pattern, how it varies in different lithology, that we use to extract information regarding other geological information. So vegetation indices, I'm coming to that. These indices are simply band ratios. And why band ratios are made use, why they are so useful? You know, as I told, every object has a characteristic trend in different spectral zones. In same object may be reflecting more light, yeah, electromagnetic radiation in one band and is absorbing more in another. So if you are taking only one characteristic and you are making map, the maximum, suppose one vegetation is there, which is reflecting red band maximum, and you are using one band then definitely you are using only the information from the red band. And suppose the same band, same pixel is characteristically absorbing more in infrared, then two parameters simultaneously if you will be using if you are taking ratio of that. In one band it is transmitting more, reflecting more, in other band it is absorbing more, but means reflecting less. So you are combining two parameters simultaneously if you are taking two bands, so it gives much more information if you are using a band ratio technique. So different techniques has been used. They are called vegetation indices because they are made to extract more information from the vegetation part. You will be astonished to know there are more than 100 such type of vegetation indices developed by different workers, but I will be discussing some of them. But fundamentals you must know how they are prepared, why they are prepared, what sort of information you can extract from. See, first one is infrared index, BVI, NDVI, SAVI, ARVI, yellowness index, and many more. What are they used? I will be discussing one by one. Some of them I have taken. Examine climate trends. Actually, climate trends affects the vegetation, and how vegetation is being affected, it will give some information about the climate trend. Examine water content of soil remotely. Monitor drought if water content is decreasing. Temporal using temporal data, if you can see that, definitely you can say something about drought. Yes, that part, in that part there was drought. Yeah, how it is progressing. Then schedule crop irrigation, when the crops are to be irrigated. Assess change in biodiversity. Classify vegetation and forecast agriculture production. On the basis of all these, you can forecast agriculture productions. So these techniques will be using. See, the most talked and used vegetation index is NDVI, that is normalized difference vegetation index. NDVI is rather it's buzzword word, every time it is being used, even geologists use. हम लोग कैसे करते हैं इसको? Actually, on the basis of vegetation type and health of the vegetation, many times we are able to pick some faults in the geological terrains, because faults have characteristic. Suppose in monotonous terrain where the water supply is limited, rather monotonous, the plants along the faults get some extra source of water. One fault zone is there, the quality of vegetation is different. So on the basis of suppose some trend is there and other information is not available, even then on the basis of NDVI, many times we are able to demark those faults. So we also use this NDVI in geological investigations. So what is NDVI? NDVI is simply the ratio of the difference and sum of the near infrared and red band. Okay, keep in mind you have to use most efficiently the reflectance data. Reflectance data is used to calculate this one. If you are using DN data, no, DN data nahi use karna hai. From DN data, if you are using even radiance data, since it is a ratio data, then it will work, but you have to appropriately you have to take the reflectance data. So simply if you are using in ArcGIS or QGIS, first you have to make one band in which you will be subtracting NIR, red from NIR, then make another band adding NIR and red, then in third operation you will be doing ratio of this band divided by this band. It will give the normalized difference vegetation index. But in if you are doing in ERDAS NV, so simply you will have to give the NIR and R. You have to define there. Yeah, system will ask which data you are using. If you say I am using ETM plus, then it will automatically take yes. If ETM plus is there, then NIR is 4, R is 3. So it will automatically calculate. Otherwise, you have to have knowledge of the spectral characteristic of the bands. Suppose band 3 is band 4 is of OLI, then it will be different from ETM. So band name pe mat jaiye, you must know which band is of which spectral range. In that way, your NDVI will be calculated. So then compares the reflectance value of the red and near infrared. Okay? It varies from -1 to +1. Reflectance हमेशा 0 से 1 तक होता है क्योंकि that is percentage of total light का होता है. So it will range always between -1 to +1. ठीक है? Higher values, higher biomass. जहाँ प्लस जहाँ ज्यादा वेजिटेशन होगा, the value will be more generally 0.6, 0.7, 0.8 तक जाता है. Sometimes where vegetation is not there, some ice cap, snow cap is there, it is around 0, sometimes -1, very near to 0. Some soil, bare soil may it will be around 0 to minus part, yeah, sometimes plus. But where it is more than +4, 5, definitely it is good quality vegetation. On that basis, you can know what is the characteristic of the vegetation type. But sensitive to the effects of soil and atmosphere. See, many times actually the soil and atmosphere also adds something to the this NDVI sensitive to these also. So there are some other indices developed which are modified NDVI. So there this disturbances from soil atmosphere has been taken care of. See, I have prepared one NDVI for north eastern part of the Arunachal Pradesh, Dibang Valley, Anja area. See here, this is the NDVI. See, it is ranging from 0.9 to plus to minus, and these red parts are low, having low NDVI, and these green parts are having high NDVI. See, this is river. And in the valley parts, the vegetation quality is better. More water content, more chlorophyll, biomass is more. That's why it is greener. Once it is going on the high parts, high altitudes, where in some parts some snow cover is also there. So their NDVI is very low. See, I have just shown you the information. This is one water body. Here the pixel value of NDVI is minus 0.03. It is very near to 0. Water, for water it is almost 0, very near to 0. And see here the quality of vegetation in the valley part, it is 0.61. Yeah, in that way you can know the quality of vegetation. It is very widely used index. Then as I told, some disturbances from soil and atmosphere, they have to be taken care of, and one new index has been developed, that is called soil adjusted vegetation index, SAVI. So these things definitely you'll be getting in different literature everywhere, but you have to know when to use, what information you are going to extract, and how to use. For that, basic principles of remote sensing is required, in which you have to have fair knowledge of the characteristic of the bands. See, in soil adjusted vegetation, what is there? It is NIR minus R divided by NIR plus red, plus into 1 plus L. L is value ranges from 1. For high green vegetation, L is 0. For low green vegetation, L is 1. You have to take in that way. If suppose L is 0, then it becomes NABI, NDVI, then it becomes NDVI. Here, if it is 0 into 1, it becomes NDVI, simple NDVI. Useful for sparse vegetation. If vegetation is sparse, the land cover exposure is more, then the adjustment for the soil is must. So keep in mind, if the vegetation is sparse, then such type of this index will be more useful than the DVI. Then one is atmospherically resistant vegetation index, ARVI, developed by Kaufman and Tanner index. Here disturbances from atmosphere is also taken care of. This is robust to topographic effects, highly effective monitoring tool for tropical mountain regions. Same thing is there, NIR and R is there, but blue band has been also taken care of into this. Actually, this is why maximum scattering is in the blue band. So the disturbances by this scattering to cater that type of disturbance, blue band has also been added and divided by into this index. This is atmospherically resistant vegetation index. Then one is normalized burn ratio. Apart from the visible range and near infrared, the thermal band, thermal infrared are right side of the near infrared. That part is very useful to monitor the anything in which heat is involved, because Planck's rule, every body which is having temperature more than the absolute zero emits some sort of energy, and that energy is proportional to the temperature of the body. So suppose one forest fire is there, that can be very easily recorded using thermal spectral zone of this remote spectral electromagnetic spectrum, because it is not reflected, rather it is emitted light that is recorded by the sensors. But since the wavelength of these thermal zone is quite high, therefore the total energy in these waves are quite low. That's why spatial resolution of thermal bands are very coarse. You can remember, if you have downloaded ever the ETM band, the 15 meter panchromatic, 30 meter is the first 4-5 bands. Thereafter thermal bands come. They have 60 meter resolution, only because the wavelength is quite high, so energy is low. So you will have to take larger area to get enough energy to be detected by the sensor. But the shortwave infrared, thermal infrared, that bands that are very useful for the detection of fire. So this is very common phenomena in forest fires are there. To monitor that, to detect the forest fires, and to monitor that, these bands are very useful. So NBR is simply NIR minus short wave infrared. Here, see here, short wave infrared part has come. You know, near infrared band is actually from 750 to up to 2500 nanometer. So that whole zone is very useful in that, especially in the right side zones. Typical use of NBR index for agriculture and forestry is detection of active fires, analysis of burn severity, and monitoring of vegetation survival after the burn. For that, these indices are very useful. And target indices, if you have the for knowledge of the spectral characteristic of bands, you can use them directly to detect this type of events in that area. If you are taking bands from this thermal infrared and you are comparing with the earlier data, definitely a lot of enhancement in the reflectance, radiating energy will be there. Then another is NDWI. Actually here water index, total water content of the plants. This is useful to detect whether drought is there or not, what is the health of plants, whether irrigation is required for that particular area, when irrigation is required. So that is called NIR minus short wave infrared divided by NIR plus short wave infrared. Anomaly for N days is calculated, say 10 days, and compared. Actually, this NDVI is calculated temporarily, say 10 days ka. So every 10 days, if you have to monitor a particular region, so for every 10 days, you will be calculating this NDWI. You will be then comparing these anomalies, how these anomalies increasing from one period to another period. Then you will be able to say, yes, this type of changes are there in the vegetation in the forest, and what measures are to be taken, what information you are extracting, accordingly you will be taking decisions. This is ranging from -4 to +4, lower than normal or higher than normal. Then to study water stress, yes, if it is decreasing, it is going in minus range, then some scarcity of water is there. So what is the region, what can be done, what steps is to be taken. Temporal data needed for monitoring, definitely you need temporal data depending on what is the and value for calculation of the NDWI. Okay, then let me see, yes, within 5 minutes I will be completing. Then some DEM applications. You know, digital elevation model data is very useful in different type of analysis. See, creation of relief map and 3D visualization, extracting terrain parameters for geomorphology, because they are very definitely they are helpful in studying the forestry. Hydrologic runoff modeling, how the hydrology is changing, runoff, if runoff is there, how the area will be inundating, where the water will be stored, what will be the area will be under water. Those type of modeling can be done using digital elevation model, because they have height, slope, different type of information. Then drainage basin monitoring. If you have to create drainage basin and its monitoring for that, digital elevation model data are very important. And there is avalanche and landslide monitoring. Many times it is not as important for forestry purpose people. This is geology and disaster management people. Precision farming and forestry, it is very useful in that also. Then flood monitoring. See, I have prepared one relief model. Cartosat dam से मैंने हिमालय के part का, in which this is the plain area, this is Himalayan part. I have prepared. You can also prepare, and you can extract a lot of information. You know, different stream can be generated using digital elevation models. That sort of information you can extract from digital elevation models. This drainage has been generated using the same digital same DEM data. From the same DEM data, we have generated this drainage. If you want to do watershed analysis, basin morphometry, all those linear and aerial parameters you can calculate using remote sensing data in GIS environment. In GIS environment, you will be generating these things. If you have to create a watershed at particular point, suppose here, what will the watershed here? It will be generating watershed up at this point. So for that, DEM models are available. The data sources and software, I just want to discuss what are the different data sources. LIS, MSS, TM, ETM, LIS is IRS data. These are Landsat data. This is TERA's Ester data. These are MSS data. Okay? Apart from multispectral data, some hyperspectral data for learning purpose, Hyperion data is available for different strips in different parts of India. For that, if you want to learn something, that data is available. Luckily, your area falls in that particular strip where for the data is available. You can use for the analysis also. These are DEM data available, SRTM, GDEM, CartoSatDEM, and all are 30-meter resolution data that can be freely downloaded. Earlier, SRTM data other than the US was 90 meter, but now from 2014-15, 30-meter resolution data is available. Lot of free softwares are there. QGIS. It is very good software, equivalent to ArcGIS. If people are using this, most of the things can be done in QGIS. ArcGIS is very good software handling everything. Even many of the image processing techniques, things you can do here also. ADAS and ELIS, they are sorry. ADAS and ELIS are specialized remote sensing image processing softwares. LVS is free image processing software, and many more. If you look for that, many things are there where you can download the data. Thank you. That is from my side. Now, I hope if some clarifications, some queries, some questions are there, you are welcome here.
On the video also.
Thank you, sir, for your nice presentation. I'm Dr. Nilay here.
Yeah, thank you, sir.
So you have given lots of information to our participants regarding our basic principles, wavelength, especially visible spectrums, structure of image, so panchromatic bands, preparation of imaginary color composites. So lots of information you have given to our participants. So I hope that that is very much beneficial to our all the persons over there. So I just request to the participants, if anyone having any questions, please ask to sir. You're welcome. Anybody from the participants having any questions? So please ask to sir.
Yes, please. Yes, some questions.
Anybody?
In the,
Yeah, no questions there.
yeah, all the participant, I'll give the privilege of unmuting yourself and interact with the resource person. Now you can unmute yourself and you can ask the question. Sir, you can disable your share screen. Why don't you disable?
You sir, you please disable your screen, sir.
You can stop your share screen. Oh, you have unmuted. Actually, I have did that privilege. So you just unmute and you can talk. See, you have to unmute yourself.
Yes.
Now you can. Yeah, sir, you can stop the share screen.
1 second. I have to stop.
Yeah,
You
there is a red color button that is stop screen. Just you can
Stop there. Yeah.
now.
Is it?
Dear participant, if you have any question, you can type it in the chat box, or else you can you can ask the question directly.
Yeah, anybody who's having a query, sir is here, Dr. PK Singh. So please, any participants?
Yeah, either they have got everything or nothing, it seems.
Sir, you have given a wonderful, sir, as I am here since long back. So I'm just listening to your all lectures. So you have given a wonderful, and I think you have just here, I think you have just carried out your whole this one program over this topic here in 14 years, I think so, sir. So it's a wonderful chance for me to just hear you. So now, sir, I think nobody is here to ask you any question. So now I shift just the mic to Purnavati ma'am for a vote of thanks, sir.
Okay, thank you. I'm actually, my email will be there. If anybody is interested, any type of query, any type of help, I'm always available. I'll be happy. Okay.
Okay, sir. Yeah.
Hello, good evening, sir. Actually, thank you so much, sir, for giving your valuable time and share your typical knowledge this evening. And I just want to thank our organizing committee, especially our Dean sir, Dr. S.K. Patnaik, sir, organizing secretary, and Dr. P. Raza, PI of NAHEP, and also the chairman of this platform. To let us all gather here and giving us an opportunity and learn about a very specific important topic, covering a sub-theme, principles of remote sensing and application in the forestry, which is recently most discussed issue with significant implementation in the future generation and can sustain livelihood for many of the farmers and younger generation, especially students, researchers, and younger scientists. Thank you so much, sir.
Thank you very much. Thank you.
You want to?
Sir, with this we conclude today's session, technical session. So I hope that all the participants will join tomorrow. We have some two important speakers are there. For tomorrow at 11 o'clock we'll meet again. All the participants, thank you. Thank you all.
Thank you. I am putting my email
thank you,
into the chat box. If anybody interested in that, definitely he may contact. Okay.
participants को बोल दो कल के लिए